Hi folks, we're looking at number 17 from page 187. So they give us this position function defined as a piecewise function, and they give you a little story as to why it needs to be defined this way. But let's go to the first question where we need to show that the acceleration is continuous at t equals 0. Okay, so we see that at 0 is where there's a change. Now from the left we can see that the derivative will be 0 and its derivative, meaning the acceleration, will also be 0. So we already know that as we approach from the left, derivative is always equal to 0. Okay, so I'm just going to deal with t greater than or equal to 0 for my derivatives here. Okay, so let's start by finding the velocity, which of course is the derivative of the position function. So let's start by using the quotient rule. So 3t squared times t squared plus 1 minus t cubed times 2t all over t squared plus 1 squared. Okay. Now since I need to find the acceleration, it's worthwhile simplifying this. Okay. So here we've got 3t to the fourth minus 2t to the fourth. So that's just t to the fourth, and then here we're left with a plus 3t squared. Okay, all over t squared plus 1 squared. So now to find the acceleration, we're going to use the quotient rule again. So derivative of the top is 4t cubed plus 6t, okay, times the denominator, t squared plus 1 squared, and then minus t to the fourth plus 3t squared times derivative of the denominator, which is 2t squared plus 1 to the exponent 1 times derivative of t squared plus 1, which is 2t. Okay, and all over t squared plus 1 squared, so that's going to give us to the exponent 4. Okay, so first thing we want to do is show that the acceleration is continuous. So I know from the left, the acceleration is approaching 0. So from the right, okay, we're just going to test if this is also equal to 0. So since all I have to do is plug in 0, and that's pretty easy, I'm not going to worry about simplifying right now. Okay, because here I see that 0 and 0, so that term's equal to 0. So I'm multiplying by whatever this is. This whole term is equal to 0. Let's look at the second part. This is 0, this is 0, and I've got a multiple of 0 here, so that means this whole expression is also equal to 0. And the numerator is not equal to 0, okay, because 0 plus 1, 1 to the fourth, so I've got 0 over 1. That means as I approach from the right, the acceleration is also 0. So since whether I go from the left or right, I'm still approaching 0, that tells me that the acceleration is continuous at 0. Okay, so we just deal with it the same way as we would have dealing with the first derivative. Okay, so that's part A. Part B asks us what happens to the velocity and acceleration for very large values of t. Okay, now here we have rational expressions or rational functions, so we know that the only thing that's going to determine the end behavior is going to be the highest term to tell us whether it's approaching an asymptote or whether it's going to positive or negative infinity. Okay, so let's start with the velocity. Okay, and we see that the velocity, as t gets larger and larger, the only thing that becomes important in the numerator is the t to the fourth. Okay, and in the denominator, we see that the highest power of t will again be t to the fourth. So this is going towards t to the fourth over t to the fourth, so which is just equal to 1. So that means that the limit as t approaches infinity of the velocity will be approaching 1. In other words, there's a horizontal asymptote. Okay. I'm going to need to do the same thing with the acceleration So I can see right off the bat that the denominator is approaching t to the 6. Okay, not approaching it, but that's the dominant term in the denominator. So I got to check the dominant term in the numerator. Okay, so I'm only looking for the highest power of t. So from here, I'm going to get a t to the 4th, and here I have a 4t cubed. So that's going to give me a 4t to the 7. Okay, and so the denominator is approaching t to the 6th. So my first indication is that this might be approaching infinity, because the numerator's degree might be higher than the denominator's. But when I look at the other side, I see that the highest power of t, well, I have a t to the 4th. Here I've got a t squared, so t to the 6 plus another t. That's also t to the 7. And my coefficient is going to be 4. So I have a minus 4t to the 7. So these cancel out. Okay? So let's see if we can figure out the next highest power of t without having to expand all this. You can see that I'm doing everything I can to try to avoid expanding all this. Okay? So again, t to the 4th is my highest power of t here. And let's skip this one because we took care of it. So there we've got a 6t times t to the 4th. So we have a plus 6t to the 5th. So already this doesn't have anything higher than t to the 6th. Okay? Let's check this one out here. So we've already used t to the 4th. So let's skip that here. We have a 3t squared and looks like a 4t. So that's 12t cubed plus a t squared. Okay, so that's plus 12t to the 5th. Okay, so our highest term in t to the 5th is 18t to the 5th. So when we look at the acceleration, okay, we see that as t gets very, very large, the dominant term in the numerator is 18t to the 5th, and the dominant term in the denominator is t to the 6th. So since the denominator has a higher degree than the numerator, this has to be approaching 0. Okay, so the limit as t approaches infinity of the acceleration is equal to 0. Okay, so what I did here is I'd made use of my knowledge of rational functions and knowing that I only had to look at the highest powers of t in order to determine what was going on with the end behavior. Okay, so that's it for this question here. Let me pan out so that you can see the full solution. Okay, and that's it for now. Thanks.